Okay, hi, Assalamualaikum warahmatullahi wabarakatuh, and good day. So today we continue again for the topic thermal management in power electronics. So we move for the next slide, which is the slide 37 in your lecture notes. I hope all of you still remember the basic of equivalent circuit, okay, to the derivation from the thermal equivalent circuit, the analogy from the electrical to the thermal. So this is very important to make you understand about the to get the value of the RTH, okay, from the junction to the ambient. So according to the heat exchanger, okay, the mounting of the semiconductor on the heat sink can improve, okay, the effective value of RTHCA by providing a low parallel thermal resistant path RTH sink. So according to this one, okay, from the case to the ambient, so how we want to improve the effective the value of the RTH, we provide the parallel of the heatsink. So according to this one, the value of the RTH CA must be lower than the value of the RTH CA. So I want to know, I want to all of you know the understanding of the thermal resistance. If the value is we need to the as much lowest as possible. Okay, the heat flow divide as follow the current flow, with the majority taking the lower thermal resistance path their heatsink. Okay, so we can divide to the two part, which is on the device and the second part on the heatsink. Okay, the thermal performance of the device heat exchanger can be represented by the equation. So I hope all of you still remember back, okay, this equation, the basic equation, which is uh, the different temperature is equal to power dissipation over the value of resistance RTH. So according to this one, you can get this equation. Okay, so this is the graph power dissipation versus the temperature case. Okay, the graphical represent this equation. They have two constraints that must be applied. So actually, okay, the negative PD, the power dissipation, or the value of temperature case must be higher to the TJ max. Okay, it is not possible. So this possible, the value of TJ must be higher to the TC. So according to this one, the graph implies that as the TC become more negative, the PD continue decrease. So according to this one, if the power dissipated is reduced if the value of the case temperature is increased. Okay, so according to this one, the value of the PD, the PD max with the TJ over RTH JC, and the value of slope 1 over RTH JC. So how it work? Okay, the different temperature is equal to PD RTH JC. So the value of PD, the different temperature over the RTH JC. So the different temperature, which is equal to the TJ minus with the TC over RTH JC. So what happened if the value of a TC, okay, the value of TC reduce, okay, the value of the TC is reduced. So what happened to the value of the PD? So the PD will be increase. So according to this graph for the device, the relationship between the PD and DC, you can see on this equation. Okay. Okay, so for the heat exchanger, this is the equation. Okay, and you just follow this standard of graph. Okay, so this one, they combine the device and heat exchanger to become this graph. So according to this one, the cross line, the cross line between the device and heat exchanger, you can get the temperature operation, and then the dissipated operation. Okay. Okay, so according to this example, so we can move for the next example there. Okay, I just skip for this one. Okay, so I want to all of you do this example. Okay, so according to this example, we do it together. Okay, let's do it together. So a semiconductor device is to be operated with its junction temperature uh, not exceeding 80 degrees Celsius, with dissipating which is 16 watt to the ambient air at the temperature 60 degree. The thermal resistance junction to case, it is specified by the manufacturer as 1.25 degrees Celsius watt per watt, and the thermal resistant case to sink using the insulator washer, and the thermal conductive compound is taken as 0.50 Celsius over watt per watt. Okay, so what is the important parameter that we have? So for the first, we have the TJ. Okay, so the value of the TJ is equal to 80 degrees Celsius, and then the second one, what is the important parameter that we have? For the second one is a value of PD, power dissipated. Okay, and then the second one to ambient air, which is the value of TA, which is the 40 degrees Celsius, and then the thermal resistant, okay, the thermal resistant junction to case, okay, RTH, junction to case, GC, 1/25 degrees Celsius of watt, and then the thermal resistant case to sink, okay, RTH, case to sink, okay, is equal to 0.50 Celsius over watt. So according to this one, we need to find, the value of sink to the thermal resistance from sink to the ambient. Okay, so we just draw again. Okay, just draw. Okay, draw again. Okay, we have the value of the TJ. Okay, from the TJ to the TC, and then from the TC, we have value of, from the TC we have a T sink. Okay, and then we have another thermal resistance, and then we have the value of TA. So according to this one, we have the value of the RTH JC, we have the RTH CS, and then we need to find the value of the RTH SE. So the value of the TJ is equal to 80 degrees Celsius. Okay, the value of the RTH JC is equal to 1.25 degree Celsius of watt. And then the value of the TC, but we have the value of the TCS 0.50 Celsius of watt per watt. And then the value TS we doesn't have, and then what is the value of the RTSSA, and we also have the value of TA, which is 40 degree Celsius. So according to this one, you still remember to get the equivalent circuit, and then the final equation, which is the value of the TJ is equal to PD RTH JC plus with the RTH CS plus the value RTH SA plus with the TA. So I want to all of you, if you don't know to get this final equation, you can refer to the video on part 1. Okay, so according to this one, the value of TJ we have the value of PD also we have 16, and the value of the RTHJC is equal to 1.25, and then the value RTH CS 0.5. okay, and then the value RTH SA we doesn't have this value, and the value of the TA is 40 degree Celsius. Okay, so what is the final value of the RTH SA? So the final value is 0.75 degree of watt per watt. Okay, so I want to all of you remember back how to get this equation on the part 1 video, and then I will share to you the tutorial. So I hope all of you can do the tutorial to more understand, okay, to get the several parameter, if they want to all of you find the okay. So thank you everyone, so all the best. Okay, bye. Assalamualaikum warahmatullahi wabarakatuh.